Good evening. How are you doing today? I hope you're fine. So in today's lecture, we're talking about floating point, floating point types. And in our last lecture, we talked about integer modifier, and I hope you guys understand what integer is and integer modifier is. Because in our previous lecture before we treated integer modifier, we treated integer, which is a data type in C++ programming language, that allows us to use or to have access to decimal number. So now when we extend our lecture, we extend it to integer modifier, so whereby we can able to modify, optimize, or manage our memory or our data or the value we have by using short, long, and long short. We have long, and we have sign and we have unsigned such a things. So they are modifier to integer, and I really kind of concluded that it is only integer that has modifier. So it is only integer that you can actually modify, that you can actually modify, that you can use unsigned, sign, and you can use negative number, and you can use positive number, that you can actually modify it, in the way we did in the kind of way that we actually can use negative number, or we can use positive number, whereby if you use negative number in that particular specific data type, or in that variable, it's going to give us error. So I think we did stuff like that, and I am so sorry. In our last lecture, that was integer modifier, I didn't really round up things where I actually missed something, very little things I should not miss. So I think I've opened the Visual Studio, so let me just go there and did some kind of adjustment actually. So the adjustment is not really much, so I can just comment everything out and make things look simple here. So we should just go to today's lectures as fast as, or as quick as possible. So now what I actually mean is that, let me zoom this thing so you can see it properly. Okay, so now I'll just bring something very simple for you guys. So we have short, or let's say unsigned, and I won't use very much. I'll use unsigned, and I'll just use number 1, and then so I can have value of 100 in this, and I have sign, and I have the value of 2, and I can use the value of 20 anyhow as I want. Or let's just be precisely, sign can just be negative number. So now let's use something else again. So we're gonna use long. So long, we're gonna use number 3, and we're gonna have long can be both negative and positive actually. So we can actually use 65 or 56, and so let's just use something else again. So what else can we use? So okay, let's just stop here for now, and if I should remember anything again, I'll bring it to you guys. So what I actually wanted to do in this particular lecture is that unsigned. So there's something I actually missed, guys. If you actually decline sign and this kind of operator, this is integer type that we actually modify, that we use only sign, and you can actually put sign int in as you feel like. Unsigned int, I mean. So you can put unsigned int, or you put unsigned, it's still the same thing. They takes 4 bytes memories, both the same thing. But I actually missed something, which is suffix. So whenever you are actually declaring, or you are using integer modifier, you should try and manage to suffix them. Suffix means by adding a specific character, like a single character at the end of it, to show or to identify that this particular value here is unsigned. Now I have 100 here, so I put U as the end of it, and the U represents unsigned. So in this particular one here, actually sign does not really have just one. So we know this is in negative number, and it takes sign memory, and long actually have suffix too. So you can also suffix long. So long, you can actually use l to suffix l and to suffix long. So whenever you use l, it is or it is, you know, seen or recognized as long. Whenever anyone say this kind of value or use this kind of value 56L, it is represent, or it actually means, sorry, it actually means long. So whenever I use something like this, it means long. And so whenever I use like long, okay, let's see, unsigned, or let's say unsigned long, and just put longs 3 or 4. Okay, we can actually use, let's just use something very easy and say we can actually use UL. So this specifically means unsigned long. Unsigned long is like I am actually declaring positive number in a long, and I'm using long. So this actually is still the same thing. So whenever you do something like this here, it's all called suffix, and this suffix is for identification, to identify your value. You know, on the norms here we declared this integer, which is unsigned long, and we declared the value of 4. That is the variable. But so, you know, make it really specific, and which C++ supports it. So you should try as much as possible to use this specific suffix, you know, to identify your variable, or your value, I mean. So if you should print this out, it shouldn't give us error. It shouldn't give us error. Sorry. It shouldn't give us errors. Everything, it should not give us errors. And I'm gonna change everything. There shouldn't be error there. So I'm gonna change the values here. I'm gonna change everything, so we can have a very snappy. So we just try and run. Let's try and run this code so we can just make it snappy. I'm very sorry, it's gonna take, okay, fine. Before I really round up everything, this is what I'm gonna do now. Oh, sorry. This is what I'm gonna do now. I am going to specify. I'm gonna list everything out for you, but I'll just try and, you know, I'll just try and run this code just to make it snappy, because we are not actually treating this specific topics today. So I'll just, you know, I'll list everything you had for you guys to go and check it out for yourself. Oh, I'm sorry about that. Sorry about this long process. And fine, with this long process, so we don't waste our time. I'll try and list everything. So we have long. So in this, okay. Okay, we have short. Though short doesn't really have suffix. We don't have suffix for. We don't have suffix for short. Doesn't have suffix. So we have unsigned. We have unsigned, which is U, which you know about that. We have U, which is U. So now I'm going to, you know, view this code in the terminal. I'm going to view everything for you guys in the terminal, so you can actually see what I'm trying to talk about. That it won't give us error because we are doing exactly the right thing. But whereby it is unsigned, but don't worry, let me try and list everything. Let me check this code for you guys. So I'll list everything we have there for you. And yep, the value is, sorry, though I didn't really give it space, and you actually packed everything together for us. We have 100. Sorry, oh god, sorry about that. Terminal actually. So now we have 100, and we have minus 20, which is this one here, minus 20, and we have 56 56, which is 6, and L is not added to it. Why? Because it is just a specification, or let's say authentication of long value. So if we should over mouse on it there, it will give us long though. And okay, fine. So now it is long on sign give us U, and we have long give us L. And when we have this, whenever you use on sign, you can actually use U on, sorry, when you have on sign long, you can actually use U and L. So you can actually use this value together. So we have suffix for on sign, and we have suffix for long, but we don't have for short. We don't really have for short. Short does not have. So even if you have long, too long, like long, like we use long, you can just use double L. Sorry, you can just use double L, and still you compiler understand that. Let's try and use it here. So if you have long, compiler still understand what. Sorry, compiler understand what you mean by that. Sorry about that. So compiler understand what you mean by that. I'm sorry for taking your time. I'm so sorry. I am very, very sorry. So actually, compiler understand that. So LL, it won't really give us error. It shouldn't give us error. So it's still the same thing. It doesn't give us error. It means that I am actually using long. So make sure and suffix your data whenever you are using it. The purpose of this suffixing is to identify your value. Even if you use just like, okay, now I use integer here. Okay, fine. And I did not use unsigned integer, but I just use 100 and I use U. On a nonce here, automatically my value will be turned to unsigned because I actually suffix it here. That's one of the purpose of. I hope you get me. That's one of the purpose of using it, because I use integer. You know, there are some situations whereby you just want to use only integer, and so you only want to use only int. You don't want to define everything, you know, to stress it, to reduce your type, to typing stuff, to reduce it from typing very long stuff. So to reduce stuff like that, you can just use int and then you put U. So automatically this is all called unsigned int. Even if you add 0, like let's add minus here. If you add minus here now, it's going to ignore that for us. Like compiler is going to ignore what we have for us. So if you run this code here, something is going to go wrong, very wrong. And yes, it's going to talk about this line we have, because here this is unsigned, this is positive value, and here I have actually add minus to it because I have actually suffixed it with U, and U actually means unsigned, which even the C+ is actually supporting us with this here, having it here unsigned. So if our code run, and it's going to give us error because so it's already giving us error here. So we are actually doing error. You see, it's giving us error in this particular part here, that we have unsigned and we have positive. We have positive value here, and we actually have unsigned. But the norm is, if I actually remove this U, if I remove this U for you and I run the code again, it won't give you error again, because norms, this is all integer can be positive or negative. It won't give it error again because integer can be positive or negative. So I hope you guys understand what that means. I'm very sorry about exhausting your time, and we should not be treating this in this lecture, but I really want to bring this to you guys so you can really understand what integer modifier is. So now you see it's built successfully because I removed my U, which is the suffix or identifier for unsigned, which is the identifier for unsigned. So now you should, next time in your code, try as much as possible to whenever you are using unsigned or to reduce your text or typing stuff, so you can just use int and put your suffix there. And if you are using long, you can just use long, or let's say int and put long in there. So still the same thing. You are still talking about the same thing. Even the the code editor is helping us out with the naming. So you see it very clear to you guys. So thank you very much, and I think that's all I want to talk about. Just unsigned and long that has this suffix, that if you want to reduce your stress of typing those much stuff, you can just use your suffix to represent it. So thank you very much about that, and let's go to this lecture. So in today's lecture here, we're going to talk about floating point type. So floating point type actually is a kind of I am so sorry, please. I accept my apologies. I mean, so floating point types is a, kind of value that supports decimal number or decimal point. So we have not been actually using decimal, and okay, we actually use decimal but not much, but we haven't really talked about that. So we said C++ actually has many data types, and we have integer, we have int, we have double, on yeah, we have a lot of stuff like that. So now in today's lecture we're talking about floating point types. So floating point types are actually value that supports decimal. So understanding the key of aspects of floating point numbers, potential challenge, and how to handle them effectively. So that is one of the purpose, or that is what you're going to gain from this particular lecture. So in the next slide here, I'm going to bring it to you guys. Floating point type they are used to represent number with fractional parts in C++ or other languages. So not only C++ actually have floating point types, we have other languages that have floating point types. So it actually supports, or it represents fractional number, fractional number, just as fractional number. You know what fractional number is? Fractional numbers with decimal points. So those are fractional number. So in C++ we actually have three types of floating point types. So we have float. So float actually has 4 bytes in memory. So we can actually have the maximum of 4 bytes in memory. That is how long it can actually take. And the precision of it, the precision is the value that comes after the decimal point is the precision. So the value that can actually be there is 7. You can actually store more than 7, and store 4 bytes in memory. So the comment is not yet to be said, or to be mentioned in this particular place, but don't worry, I'll bring it to you guys. And we have double. So double is also a fractional or a floating point types. So double actually support, or actually have 8 bytes in memory. 8 bytes in memory is kind of very long numbers. And the precision that we can actually store in double is actually 15. But due to some systems or some system architectures, some actually support 16. And it is not really let's say it's not really something that you can actually predict like that. You can actually predict it. So it's either store 15 or 16, depending on your operating systems. So if probably you are using Mac, and it can probably store 16, and it actually depends on the compiler you are using itself. It really also depends on the compiler. Also, compiler also have the effect on these particular precisions. So by default, it is by default. And though I'm gonna explain more what this comment means. And we have what we call long double. So long double support 16. It's 16 bytes in memory. So 16 bytes is very, very long data. So it's like multiple of this one, but not really. And they are really of like the same thing. That's double and long double, because yeah, kind of. But on the norms for you guys to understand, their memory, their memory. This actually store 8 memory and 16 memory norms. That is how it's norms. But in some system architectures, they are really of the same type. They don't really have much differences. But on the norms, this long is the extension of double. Like it's the extension of double. When we said long double, I said double, long double. So we just have this kind of mentality that says, okay, now this is the extension of double. So that is how it stores. So it actually stores 18 to 21, sometimes more. So like I said, it is not really predictable. It's something that has not rigid value like that. You can actually have specific value to store for it. So depending on your operating systems or your the compiler you are using, so it contributes to that. So now these 3 floating point types are the floating point types we have in our C++ programming language. So we have float, we have double, and we have long double. So these 3 parts represent floating point types in our C++. So I hope you guys understand what floating point of these types means. I told you guys 4 float takes 4 bytes in memory, and it can solve 7 precisions, and comment is not really it won't really bring up to you right now, but I'll bring that later. So I explained, or I talked about double, and I talked about the size is 8 and it stores 15, and the extent 15 actually. And there are some operating systems that actually go more than 15 or can store 16 actually, and long double so 16, and the precision can be 18, 21 or more. So we don't really have a specific value. So we're gonna see those things ourselves. We're gonna see it with our eyes ourselves. So don't really panic about that. So now, or don't panic. You don't really get that very much. Don't worry. You're gonna get that. So precision here we have. So now I want to explain what precision means. So precision is the value we have after this decimal here. You know, we all know what we have already seen. We have mostly, everyone have seen decimal number before. So we have seen 1.5. Even though your account balance usually have stuff like that. You have $5, 2 cents, stuff like that. You know, 2 cents, before 2 cents, it can be decimal number in between them. So you know, it is something that you should familiarize yourself with. So floating point numbers actually works with, or it is the value that comes after this decimal number. So this is the precision we have here. So precision, this precision we have, sorry about that. So precision we have is actually, this is the precision we have here. So the precision comes from this one here to this other one here, and that is the precision we have. So that is what precision is. The value that comes after the decimal point in a value, or in a decimal number. So that's what precision is. So I hope you guys understand what precision is now. And if I should refer to this one, so you should understand that you can't store more than 7 digits after decimal number here. You can't store more than 15 digits decimal. You can't store more than 15 digits whenever you use your decimal point, and you can't store more than 18 or stuff like that. You get me? So now in the next lecture, in the next slide about that. Sorry about that. In the next slide, we're gonna talk about. Sorry about my mistakes of word. And we bring up the floats, and we actually bring out floats. We have variable which actually have float number, and I create and initialize the value to it, which actually has about, let's count it, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. So we actually have 16 digits here. So we actually have 16 digits. So so we know that this particularly float won't really take all the whole data we have here, because in our precision here we said we have 7. It's only 7 that floats can contain. And you should carefully notice that I have this particular character at the end. So like I bring up in the last lecture, I said or in the last lecture, which is integer modifier, which I recently teach or amend recently now. So I talked about this suffix. So suffix is actually a way you can actually identify your data, that this is a float value, because if you don't suffix it, your compiler might think that you are trying to use double, and it will change your float type to double. That's how the compiler thinks. So it thinks that you make mistakes, and it can turn this particular value for you and change. Even though you use the float point, it can change the value to double for you if you're not really careful. So make sure you always suffix your value whenever you use your floats. Whenever you use the float, always suffix it, so you can actually specify that yes, I am using double. I am not storing more than 7 digits or below 7 digits after the decimal point. So that's what you should have in mind. And we have double here, and we have also the same thing here, but it doesn't have any suffix. And that's what I actually mean by this thing that is here, comment here. So it doesn't have anything we can actually suffix there. So default here, if you look at this part here, if you look at this part here, it's empty. But if you look at this part here, this part here is empty. Sorry, this part here is empty. It's empty. So meaning that we can actually use suffix. So I actually talking about suffix. So by default here it is double. By default it is double. The compiler understand double automatically, but compiler, you have to specify, you have to tell the compiler that this value here is float. Even if you declared a float type here, you have to suffix it to identify that yes, this is a float value, and your double two, you have to identify yes, this is, but double, you don't need to, sorry, you don't need to identify double automatically by customs or by default. I mean by default there it is double, it's converted to double. But long here you have to show also the same thing. You have to suffix double, make it long double. You have to put L at the end of the value to identify your character as long double. Even with the help of this, you must actually end your value with this specific character here, just to identify that yes, you are using double. So I hope you guys understand what I mean by this and I hope what you understand what data type means, which is being identifiers of C++, and you understand what variable means, and you understand what value means, and you understand what this suffix means. So let's move to the next part which is below, and here is by declaring and initializing the value. So here we're going to print it out. So we're going to check the size of every data types we have here, both float, double, long double. So we're going to check the size of every individual one. We're going to check the size in the memory one by one. So don't panic. So we're going to see the size ourselves. That's what we have here. We're going to see the size, every size we have there in the memory. And okay, so in the next thing here we have float number. So I told you guys that if you use more than the value you should use in float number, it automatically something goes wrong. Something really goes wrong by the compiler. Compiler says that you are making a mess and you are trying to make a mess. If you count the value you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is more. This is 9 digits, and this is more than we can actually take. It is more than what float number is. It should have with F at the end. Sorry, should have F at the end. So this is more than what we can take. That's what the compiler says. And yes, compiler is gonna do what it will. Don't worry. Should I say it? Okay, but the compiler is gonna chop out the memory. It's gonna chop off the others data. Now, assuming you have 1, 2, 3, 4, 5, 6, 7. The compiler is going to stop here at this 2 here, and this value here is going to know it can store jumps there, or or give it 0, or do something weird to it. But not because you have already tampered with the memory. You are already making a mess of it. You are making a mess of float value. So you should actually store 7. It shouldn't be more than 7. So 7 is the maximum value or maximum precision of float. So now if we should, in this code here we actually have float, we declare float, and we have number 1, which is the variable, and we have this specific value, and we try and add 1 per it. This here is not going to be caught by the compiler time. So compiler is going to run this code for us, but it will really see an error there. But whenever we check the runtime, there's going to be a problem in the runtime. We actually talk about types of error like that, where we explain compiler times error, and we explain runtime error, and types of error like that. But in this error here, it's not going to be caught. It's not going to be caught by the compiler. Compiler will know this kind of error, but it is kind of runtime that is going to notice that something is wrong with our compiler, because compiler is going to say, it's going to make this thing there for you. It's going to be like, okay, good, I will store the value for you wells and add this particular number. Okay, fine, you are actually going so well. And whenever you use this specific stuff, or you add 1 to, whenever you use this specific value or print it out, then you will notice exactly the jumps or the mistakes you made, which is what we call runtime error. So that's what we call runtime error. So I hope you guys understand what runtime error is. So it is not the error that we can actually notice until our data is being printed out, until our data is being printed out. That's when we say, oh, something is going on. Or when our program is being running, and our program is not going to, the compiler is not going to get the error until our program is successfully running. We just notice, oh, something is wrong, and that is runtime error. or whenever we are actually running, whenever the program is actually running and it has been run successfully, no errors, no typographical errors, and what can cause that runtime error, it is after you make some mistakes or logical mistakes or some. It's not kind of it is not like kind of typographical error. It's not typographical. So you're gonna see that yourself. And yeah, I think to this. So on the notes, and I with the knowledge you have right now, you should know that every value stores, or every value you have, or yeah, every value you have is stores in ones and zeros in memory. So your values is stored in 1 and 0 in memory. So you shouldn't really, that should not be new thing to you. So whenever value you do, or whenever value you create, you use your data types and use your variable, and they are then stored or convert to binary format, so the computer can, or the CPU can understand exactly what you mean. And this part here, we have talked about floating point numbers in memory. So floating point numbers in memory is different from the way integer is. Though I don't mean that it does not store ones and zeros. They both store ones and zeros, but in a special way. You know, floating point types, you know, is numbers with decimal number, and we have integer, or which is ordinary decimal, is their data, their values. Sorry, I mean their data types with their values, but they are stored in ones and zeros. But floating point numbers or floating point types are stored differently from the way integer is being stored, because of the precision we have there, or decimal we have there. So there is this kind of, you know, kind of complicated, you know, it's kind of very long topic that we can actually talk about. So I actually bring this link for you guys. If you really want to learn more about that, you can just go into this website, and yeah, you can actually go to this Wikipedia and, you know, go and look it up to yourself. Or if you want to understand more, I'll really drop in a particular group link, then a group link in the comment sections for you guys that want to understand more for private lesson, and I'm going to explain that for you guys that want to understand more about this. So because I'm not going to talk about this in this class, because it's going to take the whole time. It's going to go take the whole damn time. This is a very long topic to talk about how our values, or how our values is treated, or how our floating point numbers in memory is being treated or represented in the memory. It is not the way integer is or represented, it's the way floating point type is in the memory. They are kind of in a special way, but they are of ones and zero, but in different way. They are kind of a special method of, or ways of being represented in the memory. So is either you check it yourself, or I drop a group link, or definitely I will drop a group link in there, so we can actually, you know, chat privately, or we can talk, or, you know, kind of take a very private lesson, so you can actually understand this topic, or you can actually look these things up yourself in the Wikipedia. So thank you very much. Let me go to the next slide, so we can actually talk about this one. So yeah, we have scientific notation. So this scientific notation is a kind of, you know, don't worry, let's just relax. Okay, don't really get panic like that. It's not really hard. Scientific notation is a kind of way whereby your large sum of number or small number is being treated, or is being treated in a way that can be written in a very short way. You know, when we have this specific large sum of value here, and yeah, in scientific notation is being treated like this. If you should move to the next slide, I have this kind of things explained there. So scientific notation is handy something, because it's handy, it's very easy, you know. It is, whenever you know scientific notation, it is easy to use whenever you know scientific notation, because it's going to help you when using floating point with large sum of number or small number, but mainly or specifically it is specifically used for large number actually, or large decimal, or large number actually, floating point number, I mean. Oh, sorry, it is used with large number, I mean. So large number or small number. So it make it easy for you to write a large number or small number in a very simple and easy way, without writing a lot of digits. For example, we have we have this specific long value, we have this specific millions. Okay, yeah, it's about 193 millions and stuff like that, and everything. Sorry about that. Sorry about that. So and everything here can be bring up or can be bring into this specific value we have here, which we have here. So this value we have here can be bring into this one here, which is 1.92320, and the only difference you usually see there is that the decimal point number is there and 93, and it's kind of different, and you guys can be confused what's going on. Okay, fine, this is what's going on actually. From the explanation here I described there, if you have a scientific, okay, we're gonna use calculators to break this thing down so you guys can really understand what scientific notation is. So I'm gonna use a notepad. So I'm gonna use a notepad and I'm gonna define, okay, notepad, where are you? So now, sorry. So what this means is that E is what we call an exponent, or sorry, E is 10 to the power of 8. We have 1, we have 1, 2, 3, 4, 5, 6, 7, 8, and 8 is the value we have after 1 year. And even if we have decimal point there, so 8 is the value we have. So we're going to say 10 to the power of 8 to get this particular value we have here, or sorry, to get this particular value we have here. So we're going to get 10 to the power 10, which is E to the power of 8. So with this value here, we can actually get this specific value here, and this value are the same value in the memory. So we're going to see that, but we're going to calculate that ourselves before we do that. So now we have 10 to the power of 8, 10 to the power of 8. So what we're going to do, that is going to do this particular number multiplied by 10 to the power of 8. And you know that 10 to the power of 8 should be 10 times 10 times 10 times 10 times until it gets to 8. So we're going to do that 10 times 10 times 10 times 10 until it gets to 8. So we're going to do 10 times 10 and 10 times 10, 10 times 10. So let me going to sum this up. 10 times 10 times 10 times 10 times 10 times 10 times 10. So this is a standard form. No, in our calculator we have standard form, and we have scientific form, and scientific mode, and we have standard mode. And now we want to convert the scientific mode we have here, this particular short data we have here. We're going to convert it to standard mode that we have. We should have norms and 1, 2, 3, 4, 5, 6, 7. It should mean 1 and times 10. So now our calculator is going to really help us out in doing this, so we can actually have no error while doing the calculation. So calculator is going to help us with that, and I want to bring this so you can understand what this this scientific notation means, how you can actually store this easy number here, the scientific notation here, in order to represent the value we actually have here. So like I said in this particular slide here, we said scientific notation is an handy because it makes it easier to work with a very large or very small numbers without writing all the digits. So it makes us to write or to work with a large numbers without writing all the digits we have there. So now we're going to break these things down. We're going to break it down so we can understand what that means, what that scientific notation means. And now we're going to say 10 times 10, and 10 times 10 is going to be 100. You know that. So let's clear this off. So you know that's going to be 100. So times 10 times 10. So now I'm going to clear to 10 away because I did it twice. So now we're going to say times 10 times 10 again, times 10 times 10 again. So I'm going to take 10 away again. So I'm going to say times 10 again, times 10 times 10. So now this is gone. So fine, I'm going to multiply this particular number here, this 100 million I have here, with this value I have here, with this other value, with this specific value I have here. So now I'm going to do, what am I going to do is, okay, let me just go back to this place. What I'm going to do is that I'm going to multiply this other number I have here. So together here, I'm going to get this specific value we have here back. I'm going to write times 1.932, sorry, there's error, 9320091. So now if you get this, it should give us exactly the value we have here. You see the value we have 9319332, we have 193, exactly the value we have here. That is the value it's beginning. If you check it very well yourself, so we're gonna see, except that we didn't put 1 here, 0 here, so there's kind of 0 here, so that's one of the difference there. I think there should be 1 0 there. Okay, so that's just part of it here. We can actually add 0 there, and yeah, so that's what this means, and that's how we can actually represent this specific value we have here in the memory. So that's about scientific notation. I hope you guys understand that, and we can actually write it this way, that we can make it very handy, or in a very short form, that we can actually write it up to here. So this value times 10 raised to power 8, so we give us this value we have here. So the same thing, but this one here is different. This here is different because here we have 0 0 here, so it's going to be 0. I have the scientific notation here, and I have the standard mode. Yeah, still, yeah, I have the standard mode here, and they have the scientific notation mode here. So we have 0, we have 11 0 here. So we have 1 2, sorry about that. We have 1 2 3 4 5 6 7 8 9 10 11. So after the 0 here, after the number we have here, the next number is going to be 2, and it's going to store or indicate the decimal number after the digits we have after 0. After 0 here is going to be 2, so 2 is going to have the digits, and it's going to store the value like this. So it's going to be this value raised to power 10 minus 11. No, instead it's supposed to be, here we have raised to power 8, but here it's going to be minus 11, just because we have it in this method. So that is the reason why scientific notation is going to be like this. So I hope you guys understand what scientific notation means, what standard form, and the scientific notation means, or what the purpose, which is the purpose is for you to make it easier for you to, make a very large numbers or very large value, to you make it in a very, or you're gonna customize it in a way that you can write it in a very little way, or in a very way that you don't have to stress yourself very much. So that's more about scientific notation, and and standard modes which we have here, or the actual value we have here. So, and in our next slide here, we're gonna have something very, very strange. So we have what we call infinite and none. So infinite and none is a types in floating points types in memory, or floating points value in memory, or characteristics in memory, because every float point value actually have infinite and none. And what did I mean by infinite and none? None. So infinite actually is every value you have here, or any value you have here, divided by 0 is going to give you infinite. So any value you have here, any floating level here, maybe you have 7.5, 8.5, 2.3, 39 point something, stuff like that. So divided by 0 is going to give you infinite value, infinite in the memory. And whenever you have 0.0 divided by 0.0, anything divided by 0.0 is what called none, which means none, like nothing. It's nothing, definitely nothing, like emptiness. And this infinite is like extension of value, like infinite. So whenever you define any value we have here, divided by 0 is going to give you infinite in the memory. So that's all. In the value is going to be infinite, and you're going to see those things here in the next lectures. Here we have very simple stuff here, and sorry about taking very long. So here we are printing the size. Here we are taking none, and we didn't really make none. There was error, not really error, like, but I'll adjust that. I didn't really complete the tutorial for. So let's say we have double, and we have okay, no, it's fine. I didn't really complete the so it's supposed to be fine. It's supposed to be 8, which is divided by 9. So we're gonna make 9, which does not have value. Sorry, I'm gonna explain this. Sorry, let me finish this stuff. Let me finish it first. So now, what I actually means here is like I am actually printing those things in the memory. We are still talking about none and infinite here. So none and infinite, actually we have value of, there's blunder here. So now we have actually the value of 8.3. 8.3 is a decimal. This is a floating point type, which this decimal point here is a specification that there is a floating point type, which is fractional number. And fractional number here we have double, we have double data type, and we have variable. And what we actually, we did not give it any value, so it's going to be initialize it. Your compiler is going to initialize it to 0 because you didn't give it any value, so it's going to initialize same thing to 0. So here we're going to get the result of none. Infinite. Here it's supposed to be none. Yep, yes, supposed to be none. So now in this particular value, in this particular section here, we have infinite, and here we have double, we have results, we create a variable, and we do the division of 7. Here we have 8.3 divided by 8. Actually 8 is 0, and 8.9 is what? 7 is 8.9. 7 is 8.9. I'm sorry, 8.3. I'm very sorry. 8.3 is 7, and here is 0. So we are dividing floating, which is this floating points divided by 0, and that is exactly what we are doing here. Floating point types divided by 0. So we're gonna get infinite in our. You're gonna see it yourself. So 7 divided by 0, and sorry, this is just a string character. And here we're going to see it here. We have already do everything here, which is in the result. So we're going to see it print out in the memory result. And we have result the plus 7. So result is the value we get from the infinite, and plus 7, which we have here. So it's going to give us the same thing, which is infinite. But when we get to this specific place here, it's going to give us none, because whenever you divide any value which is 0 by 0 with floating point types, it's going to give a none, like emptiness. And those things are really taught in, they are really specialized or specific, like they are really treated or understand in this particular section here. But I won't be taking this because it's going to take a lot of times like that, so I won't really be taking that. If you only want to know more about that, know exactly the reason why it's infinite, is infinite or none, I'm gonna drop a WhatsApp link or on the comment section there, and you guys can just make a private chat, and I'll be actually explain more about that. So okay, that is more about this section. We're gonna see those things in code. Okay, fine. Before we actually round up with this section here, so remember the suffix which when you initialize in the float value, otherwise it is default. It will be default by otherwise the default will be double. I actually bring this in also here, so try and understand that whenever you did not suffix the value, your floating point types here, floating point types is going to be double. it's going to be double by default. By default it's going to be double. So yeah, whenever you do not suffix, no, I suffix this one with F, I suffix this one with L. If you do not suffix this, automatically it returns to double. Your compiler will change that to double for you because you do not suffix it. So make sure you suffix your value whenever you are using it. So that is one of the notes I want you guys to be aware of. And double is very important in many cases. You will see that, like, we're gonna use a lot. Double is very important. It is very important in all calls. It's very important and very important. And why does precision matters? This precision you are seeing there, why does it really matters? And this is just a number that doesn't really matters. 0 after 1 and point 0. After 1 dot. This doesn't really matter. So the norms real life norms number. So you know that after 1 should be 2, and every number that called or that has occurred before 2 in a real times number is really junks. Something that doesn't really make sense to us. But norms here, we should understand that every value you have here, they really matters. Every value here there matters. Whenever we are talking about scientific computing. So if you're working with scientific computing software, it really matters. Every bit of this precision, they really matters to you. You should try and be careful with that. There was a time I was trying to make a game shape, and I was actually trying to make a very shape, and I was trying to calculate the direction of the of the character, and I really make just like a very little adjustment with the precision. Just the precision. Actually, I didn't really touch the actual number. The precision, do you understand what the precision means? The decimal point, sorry, you understand what the precision is after all. So I really make mess with that, and it really affects. I really see it myself, like it affects the character movement. So also in scientific computing, like you are working with, maybe you are trying to make a weather stuff, or you are trying to calculate the forecast and stuff like that, you should be aware of, you have to be very careful whenever you're using precision, and you have to be take that as a very important course or important things for you to know. And you are working with game development, precision is important. The direction of the bullets, the size or the speed of your character, every dense stuff there really matters when you are using it for game development. For stimulation also, you are creating a graphical simulation, like stuff like that, they really matters there. And mostly this precision here, there matters in kind of whenever you are using for graphics kind of computations there, you're using for graphics or simulation stuff and gaming stuff like that, they really matters. Not only that, there matters in every round 3, and other field precision matters in calculating critical things like that. They are all matters. So you guys should get and try and put that to your understanding that, or your knowledge that every precision in your value or your variable there really matters whenever you're having floating point types. So I think that's the end of this particular part, and let's go to our Visual Studio and let's do something. Sorry about that, exhausting the time. So now let's just draw cond. Okay, I think I have okay. So okay, I have some kind of stop opening here. Okay, good. So now I'm gonna write cd and go to the part and code. So in this part here, we'll be talking about floating point times, and let's try and do something very rapid. And I'll be copying some of the codes so to make it really snappy, and I'll be copying some of the codes. Of course, I did it myself. you should go and type yours too. Okay, good, thank you very much. Okay, so I'm going to be copying this, and I'm going to be copying this one I have here. Or let me just make some simple adjustments there. I want to make some adjustments in this part here. Yep. So yeah, error. The adjustment I want to make is that okay, no, I'm not really making adjustments. I think it's fine like this. So now here we have floating point types here, which is the first thing we talk about. We talk about floats, and we know that float stores, or we are taught that float stores 4 bytes in memory, and we can actually store 7 precision here, not this specific precision we have here. And here we have we have suffix of f here, so we can actually you can either use capital letter F, or we can usually use just small letter F, anyone you feel like using. So it's okay by the compiler actually. So now we have double, and double is default, you don't need to add any suffix there. So non double, here we have the variable and we have the value here, and we can actually suffix it with L. So now let's try and print something, and let's try and copy something again from this part here, and to make it really very easy for us to run this stuff. And so we're going to be doing something very simple here. So now I'll be adjusting this stuff here. There's error here. This is no good. Good. So now this is a very good one. So now let me try and explain what this is. Of course you understand what this means, and this is just to check the size of this value in memory. You want to check the size, but before we check the size, let's try and print the value. Let's try and print the value first. Or which one should we do? Let's try and print the value, and let's see the precision. Actually, we want to check how much they can contain in the memory. Or first, let's check the size first. Let's check the size first. So let's build with tags, run build tags, and let's check that first. So let's use GCC compiler, and after GCC compiler, so we're gonna check the size. First thing, we're gonna check the size and the memory, and after that we're gonna check the precision. Oh, this is what I don't like about this thing. It's gonna take some time. Okay, good okay, fine. Fine. So in this part here, you're gonna read or see what we have in our code from the part here. So now this is exactly very good, very good. It's very good. So now you see exactly what we have here. We see that in this part here we have 4 bytes in memory. We have 8 bytes. We have 16 here. But whenever when we go to our stuff, we have 16 also. We have 16 actually. The precision is 16. So the size, sorry, I said precision. The size in memory is 16. For non-double is 16. So for double is 8, and for float is 4. So that is the maximum value that can be stored in every data types you see here, which is the floating point types you see here. So now let's try and clear this up, and let's check the precision. That's the value that we can store in part of, like, how many precision we can store in every one of these we found here. So now let's go to the next one here. So what we're going to do is that we're going to call up one specific function, what we call precision. We're going to do xtd set precision to let's say to 20. So this is going to control our inputs. So it's going to control our the inputs for our floating point types here. It's going to check. It's going to control the inputs we have here. So whenever we declare this before this specific data types here. It's going to control the precision you're going to get out of it. So whenever you want to use your precision, you should make sure you use these specific data, and but it's giving us kind of error types here. The reason is that because it has its own library too, so we should call it library. It has its own library, so its library is IOStreams, IOManip. So this is its library here. So it's library. This is a specific library for this specific precision. So it's not bringing any color stuff, any error stuff anymore. So the library is here also. Is here actually. So now we're gonna be printing out every data. Sorry, every one we have here, and let's check how much they contain, how many precision they have. So now I'm gonna have we have floats number. So we're gonna check float number here. So precision, let's just say float number, and we're gonna check double number also. So we're gonna check out for long double also. So now we're gonna check those things. We're gonna see those things are long double. We're gonna see those things ourselves. Sorry for taking that slow stuff. So long double, okay, fine, good. This is very good, and let's just make it really snappy. We have this precision of 20, so we set it maximum. We set it more than we have here, and let's see how much they could contain. Like how much they could contain. We have about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 here. Let's store more than 16, or let's store more than 16. Let's just add more value to it, so we can actually look for size also. We can actually check. So I stored, oh come on, I make error. Ctrl Z. So let me just write 111 here, and let me copy it. Copy, paste here. So now I had about 16, 17, 18, 19. So I had about 19 number there. That's enough. So now we're gonna check how many precision every value can contains in the memory, or in memory. So now let's just try and run it again. After we run it again, we're gonna check the precision, the size of the precision actually. Okay, it's running behind the scene. So I hope that's not bad enough. That's really going along, and I am so sorry. Okay, fine, good. So now let's try and check what those numbers there, what value these things are in memory. Oh, good. So now let's try and get carefully check those things number value now. So we have 1, 2, 3, 4, 5, 6, 7. So now let's check the value after 7. So it's supposed to be 5. So we have 1, 2, 3, 4, 5, 6, 7. So this is supposed to be 7. Okay, let's try counting again. 1, 2, 3, 4, 5, 6, 7. 4. Stop at 4, and the next value should be 8. But yes, sorry, the next value should be supposed to be 7. The next value is supposed to be 7, which is this one here, and too much. Okay, now the next value is supposed to be 7, but here it is 8. Yes, every data here we have here is chunks. They are all chunks. It's meaningless because we have stored more beyond what we can store in floating point types here, and it's giving us junks. So from 8 to 3 is junks. They are not actually following the instruction anymore. They are going wrongly. They are working wrongly. So now let's try and go after double. So now let's start double. 1 2 3. Okay, let's try and here. Okay, 3 3 4 5 6 7 8 9 10 11 12 13 13 is still going. No, it's not going anymore. Okay, let's try and count it. One. Oh, let's try and check it again in the memory. So is what? It's 15. Let's try and check it. Let's try and count it again. So after 15 we stop. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. Yep, 0 comes here, and after 0 is supposed to be what? 1, but here we have 0. So junks, this data here has junks. They are junks, so you can't store more than this data we have here in your double. So whatever comes next is junks. So this value here, they are junks, they are not printed out. So now let's move to long double and let's check how long double treat our value. So I think long double is really doing 9s and 9s and 9. So now let's check it again. Let's check double. 1 2 3. Okay, I think it's 18 or 21. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19, and let's count it here. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19, and long double actually walk through it. You see that long double walk through everything. So that's just one of the the advantages of this thing of floating point, of actually long double. It really work out through everything for you. Actually we can actually predict it, because we said it is either to be 18 or 21 or sometimes more. It is not predictable actually. So now it really prints every data we have here. So round of applause. So long double actually very good. Long double is going well. It's doing well actually. So now this is really nice. This is really nice code. I love the way it works this way, and that's very nice. So long double printed every data we have here. Nice one. And if we go back to our slide here, the next one should be okay, let's go to when things get wrong with prediction. So let me comment this out. If possible, let me comment this out so we can reduce the. So now assuming we declare new float and we do number 1, and we do something more like 1 2 3 4 5 6 7 8, or let's just copy the data we have here in case we just make mess. So now let's just do copy and paste the data we have here. Okay, good. So now this is capital. It's supposed to be a small form. So now there's actually error here. It's giving us immediate error because I stored. Okay, because I use curly brace. Actually, curly brace doesn't really allows any types of any mistakes. Curly brace in initialization is really careful to be used. I think the other day we use curly brace to declare floating point number, and we use for integer. It declares, it shows error immediately. So now let's use functional initialization. Should not give us error. I guess. Okay, let's use functional again. It should not really give us error though. Where do we get things wrong? Okay, fine. This is really error. Okay, it's because I added the suffix there. Because I didn't really add decimal points, and I didn't really add, so I just I'm coming. Let me just try and bring it from back. Okay, still okay. Okay, just because I didn't really I see it has changed it to it has changed the value to float. One of the advantages is it's already float in it, it's already changed float because I didn't suffix it. If I should suffix it, it will give me error because I didn't put decimal fractional number here. So if I should suffix it here, oh sorry, don't get me wrong. This is a float, this is an integer because see in the code editor is saying that this is an integer value because I did not put suffix here, suffix of float here. If you should go back here again, it is now float point because and now it's giving me error because I didn't add this specific decimal points or fractional decimal points number decimal points here. So that's one of the reasons giving me error. So now this is definitely error and something is going to happen just the same way it happens to I think this thing should be work out like this, also work out the same way in this one we have here. So also the same way we have it here. So let's just finish it up and let's say 1. So now let's try and print what we have here and let's see what's gonna happen to our programs. Let's see how it's gonna treat our programs we have here. And yeah, something is gonna go wrong because we have more than 7 here. We have about 1, 2, 3. I think it's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 precision here, and float takes 7. And something is going to go out here because even if you haven't adding 1 to it, so something is going to go wrong here. So whenever the compiler run it, we won't get compiler error, but we will get runtime error because there's going to be errors in our runtime that we have. Did something wrong in our programs. It's going to be like we did something very wrong in our program. Then the only way we can adjust it is by avoiding or changing something there. So now I see what it gives us here. It gives us something very bad. Yeah, it is like it's added 1 to it, and the 1 is added to this particular specific one we have here. So 1 plus 1, this is just an integer value. So it added it successfully. Fine. It adds for us together and it makes it 2. So 2.9, and it stops at 7. 1, 2, 3, 4, 5. So it doesn't even get to 7. It stopped at 5, so it's really bad here. It's something really is going here. It's going on wrong here. So now we know where our conflict or our problem is or issue is. We shouldn't declare more than the precision we have here, but here we only have just 5 value we have here. Stop at 3. Stop at 3 here, and the others value here is they are printed or thrown somewhere else, and it stores to years for us. So something is going on here. So you shouldn't do something like this and try and use exactly the precisions, and don't use more than precision whenever you are using a value. So the excess of using floats for is to minimize the way you control your value, not by using excess of the memory. You declare float double and you're using just little data. So that's not making sense. So that's one of the reasons. And let's go to our problem and let's try and check what's going to happen in the next slide here. So yeah, we're going to be talking about scientific notation. I'm going to copy what is here. So yeah, we're going to copy, going to write I'm not sure that's what this correct. Should have copied that too. Okay, so now we have scientific notation, and every value we have here is going to give exactly what we have here. What we have here is going to be the same thing we're going to have in the memory. So if we should print this thing out one by one or at a time, we have number 1, number 2, or let's try and put this in a ring count. So it's gonna be number 2 and number 2. So we're gonna print everything, and you're gonna see to yourself that all the value we have here is gonna be exactly the same thing we have in the memory. So 6, okay, good. So let me try and change them here. So now good. So every value here, sorry, from here to this particular value is going to be the same thing. So this is going to be the same thing, and here is going to be the same thing as well, because this is the scientific notation for it, and this is the standard form. And I actually explain what this means. And let's try and run the code and let's check. So let's try and divide what we have here. Not make that comment. So good. And now I'm going to run the code and see how the scientific notation works. And I think not really much. So it's really taking time. Okay, good. We didn't really print that out. 10, something is wrong. I think there is error. There's kind of this is more than 8. There's error in this actual code, so that is one of the reasons it's giving us kind of error. So if we should check here carefully, I think it's more than 8. 1. So let's try and count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9. So let's try and remove just single 0. So single 0 and single 0, and okay, let's try and run it again, and it's really getting well run. Okay, we should check that again, and let's try and check what we have again. Okay. Alright, fine. The same thing. Just a little different. The same thing. What's going on? Okay. Oh, something is wrong. I am so sorry. I have forgotten. The other time when you use precision there, we didn't print our precision out. We actually comment our precision. So that's one of the reasons why we comment our precision. So let's try and uncomment our precision. So if we should uncomment our precision and run the code again, it should be able to print out. It shouldn't print this exact data for us. So we comment our precision. That is exactly what's wrong with the code. Why it's not giving us the old data, and let's try and run it again, and it won't give us this data we have here anymore. So I'm so sorry about that. It is just I forgot that I comment this restriction, and I need this restriction here to get out the value we have here. So it is the restriction that actually stops me from printing this particular data I have here. So if you should run that with the restriction, you should be able to see everything we have in our code here, programs here. So I am so sorry about that. Okay, good, very good. I like that. So now our problem is being solved. We have no issue anymore, and um, exactly fine. This is exactly what we expected. We expect, so we have the value we have here is exactly the value we have here. You see that it's all the same thing, both the scientific notation and sorry, this is the standard mode standard, and this is the scientific notation. So both the scientific and the standard, they are all the same thing. It's just that the way it is written is different, and here is also the same thing, just because it chop up the data we have here in front, which is this 9 and 1. It chop up the data, so it is still the same thing, but it's just that it chop up the data, and that is exactly what's wrong. So here we actually have um I think there is something wrong with this code. There should be something wrong. Let's try and count. If it is up to 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Actually, let's use. I'm coming. Let me use 10. So maybe I have print more than the data it should be there. So let's try and use 10. So that's more about this scientific notations and conversions to standard mode, or how we can convert your standard or your I number or I value to scientific notation, to make it handy for you, to make it easier to be written, or to just wrap it up in a very easy way, or in this kind of method that you can actually write it up or wrap everything up actually. So now, okay, the only thing we could just check about is this. Okay, good, still the same. Because it's actually 11, so it's actually 11. There's no error there. So what happens here is that it's there's no error there. There wasn't error before, but now there's error. There shouldn't be error there. What happened is that it's print the whole precision for us. It prints the whole precision for us, like we have here. This is just the standard or the normal method we have here, and here is the scientific notations, and the actual value we have here is just the same value we also have here. So it's giving or printing everything out with the help of the scientific notation, or sorry, with the help of the precision should be our help, and precision is really helping us. And sorry about the slow, and precision is really helping us, and by this method here we can actually write this code with the code we have actually sorry, the value we actually have here. We can actually wrap it up in this way. So if I should try and clear this up, and okay, they are just the same thing. Say that this having 9999 stuff like that. So actually the value we have here, just take the value we have here is the value we have here is the value that is here, as we have up here. So we check it very well, and the precision of double is just it's not about 16. Maybe we have more than 16. Oh, sorry, we have 11. It's not 16 actually. So it's so that's it about doubles, and having this type of format here. This is how it's going to give it or print it out to your consoles for you. And that's everything I think you should really know right now. Right now, this is what you should know right now. And let's move to our last section, which is the infinite unknown. So let's divide our string. Let's divide our print statement output. Let's divide our output. So now I'm going to be talking about infinite and none. So none. So yeah, we're going to have it, and let's check our program here. So now let's copy this code we have here. So it's going to make it very easy for us to wrap things up easily. Oh my god, errors, plenty errors, very plenty errors. So now we adjust that ourselves. So we actually did the value we have here, 8.3 divided by 0. This is supposed to be 0, and the yellow, this is just the yellow, it's going to yellow, and the result is going to be infinite. It is going to be infinite, so we're going to have infinite here, and this way we're going to have the result. Oh, there is error, there's error here. I used results, I didn't add s here, I am adding s here, so that's typographical error or compiler error. So now I have oh, sorry about that. So now I have results, and I'm adding this together, I'm adding the results and the infinite we have here. So it's going to give us infinite the same as well. It's going to give us infinite as well. So now adding this together, and we have results. Okay, and we have none. So we're going to have 0 minus 0. This 0, so I have 0.0 minus 0.0. That's what's going to happen here. So we're going to have here, and so that's what's going to happen here. So now we're going to have okay, we're going to divide these two together. This is going to be division, not addition. There's error there, there was error there. Now yes, I've fixed things. I think I fixed things here. I fixed things here. So now I'm gonna print this for you guys to see what's gonna happen. Or let me just try and, okay, good. And now let me just try and run this. So this is variable, and the data type of double, and we have this value of 8.3, which is actually initialized. We initialized 8.3, and here is 0 because we didn't initialize anything. 0 as well, and we declared a variable double, and we divide 8 and 8, 7 and 8. 7, that's 8.3 divided by 0, which I said is going to give you infinite. And you're going to see those things in this printout statement here, in this printout statement, and here it's going to be 0 and 0. So we're going to have 0 divided by 0. It's going to give us none as well. So now let's try and run it, and time is really going on. So if we should check this out, okay, fine, and sorry about that. I should check those things out and end this class as fast or as soon as possible, actually. Okay, good. Like, this is good. Yeah, just because of the position I see out there, just because of the position, that's one of the reasons why I have this specific value here. So this is what I'm going to do. Let me comment those things out. I'll comment this part out. I'll comment everything here. I'll comment it. So I'll comment this part here, and I'm going to run that again so you can see that code is not really clean. It's not really clean. Okay, fine. So now let's do this thing quick and clear this thing up. And we're gonna have this. Okay, good. Now just because I actually cleared the positions and I don't have anything in the front anymore. So now I have 8.3, which is this one here, and I have divided, which is this division here, and 0, and and it gives us what? Infinite. This is infinite. So this is the result to give us infinite, and we also did infinite plus 8.3. and it give us it give us infinite as well. So anything we divide by like the value we divide by infinite, or we divide by every value we divide by zero, it's gonna give us infinite. So now infinite, so this is giving us infinite. So any zero anything we divide by zero, zero divided by 0.0 divided by zero, is gonna give us none. So this is it here. So I hope you understand that. So if you want to understand that more, that's you have to go and look up to this lecture we have here, which we have. Sorry, if you want to understand more about that, you can just go and look up to this specific topic, and you will understand more about that. Or you just paste your comment section there. I'm gonna leave the group link so you guys can chat up and do that in a private way, because this is going to take a very long lectures, and I'm very sorry about that. Thank you very much. Bye.